Hi, Chris Good here. This is part one of our introduction to the analysis of variance. And our example for the statistic comes from a 1993 paper. And this is a paper in which something called the Mozart Effect was first described. And if you haven't heard about it, it's this idea that listening to classical music increases, at least for some time, your spatial IQ. And later on we'll talk in class about what exactly that means. But for right now, let's just leave it at that. Listening to classical music may or may not increase your spatial intelligence quotient. Anywho, these are the actual data, and this is the paper Rasher, Shaw, and Kai, 1993. And basically what they had is students were listening to either music, and this happened to be a Mozart piano concerto, or a relaxation tape that's, nature sounds or meditation type stuff, or they listened to nothing at all. And we compared these three groups. So these are the actual data from the paper, and what I've done is I've simplified these data so that we can just use smaller numbers and use them as an example. There were, I think, 36 participants in the whole study, but let's imagine if we did it this way with 15 different participants, 5 in each treatment group. 5 of them listened to Mozart, 5 listened to the relaxation tape, and 5 listened to silence. So what I've plotted here in the table are scores from each of the 5 people in each of the 3 groups. So we have 5 scores for people listening to Mozart, 5 listening to relaxation, and 5 listening to nothing, and I've plotted their averages there. All right. So really what we're interested in are the means. We want to know whether these means are significantly different from each other. And you already know a way that we can test that right now because we've been doing t-tests for the past 3 or 4 weeks. So we could, for example, do a t-test to compare this mean in Mozart of 4.8 with the mean in relaxation of 3.6. We could do an independent groups t-test, and we'd find out whether these are significantly different from each other. But we would also want to know whether Mozart is significantly different from silence. So we'd have to do another t-test to compare those two means. And the problem with that is that every time you do a t-test, there's a possibility that you'll make a type 1 error, that you'll reject the null when it's actually true. And when the null definitely is true, even though you'll never really know whether it is or not, when the null is true, you will make a type 1 error 5% of the time, or alpha percent of the time actually. So we usually work with an alpha of 0.05. So that proportion of the time, you're going to make a type 1 error even when the null is true. Now, if you do 2 t-tests, then you've doubled the probability of making at least one type 1 error. We'd actually have to do 3 t-tests because we'd also want to compare the relaxation mean with the silence mean. And that's just too much error. What's that you say? Why not just reduce alpha even further? Well, maybe so, but then you're increasing the probability of making a type 2 error for each individual t-test, so that's a problem too. All right. There is another way. It's called the analysis of variance, and the goal of this lecture is to show you what that is. So consider these 3 means: Mozart, relaxation, and silence. Forget about the scores for just a moment. Just look at the means. And why are these numbers different from each other? Why did the people in the Mozart group get 4.8 and people in the silence group get 2.6? Well, obviously we think that there might be an effect of what they're listening to. So that's one reason why there is variability among these 3 numbers, why the numbers aren't different from each other. But there are other reasons too. One other reason is that the way that we've described this experiment, there are different people in each group. Different people listen to Mozart. There are 5 different people in the relaxation group, and 5 completely different people in the silence group. So individual differences may play a role, right? People are different, and they have different IQs, and those differences may have existed and affected these data. All right, so those are two sources of variability. Maybe a treatment effect, the fact that people are different, right, individual differences, but there's a third sort of major source of the variability among these three means. And that is just random chance. So look at the score in number 2 under the Mozart condition. Somebody's got a score of 7. Maybe they got that score of 7 because they watched Jeopardy the night before and they were inspired, or they had a really good breakfast. And look at the person in the silence group who scored just a 1. Maybe that person's having a bad day, or they didn't get their coffee in the morning, or something like that. So these are the three sources of variability among these three means. Maybe a treatment effect, people are different, and other effects of random chance, right, that are beyond your control. So those are three explanations of why we don't have the same means. Now let's look at the individual scores within each group. Take the Mozart group, for example. Just the Mozart scores. How come everybody didn't score the same in this group? Well, it can't be a treatment effect because they were all experiencing the same treatment. They all listened to the same thing. So that's not an explanation for why these scores are different from each other within just the Mozart condition. But, as you might have guessed, these scores come from different people. So, individual differences contribute to the variability of scores within this group. That is, one explanation of why everyone didn't score the same is just the fact that people are different. And I know what you're thinking. Yes, random chance, other effects of random chance also play a role. Again, maybe this person who got a 4 down there at the bottom just really wasn't into it, got distracted, saw a squirrel out the window, and maybe the person who got the 7, again, was inspired the night before, or read something in the paper, or just was really into it, and other effects of random chance also play a role. And the same thing goes for the other two groups. So in that silence group, there's variability among the scores. What are the explanations for that variability? What are the sources of the variability? Individual differences and other effects of random chance. All right. We can measure the variability of these three means, right? In a number of different ways. We can look at the range, the highest minus the lowest. We could look at the sum of the squared deviations of each individual mean from the average of all three means. And that number would tell us how variable these means are, how different the means are from each other. And again, the reasons that they're different from each other are maybe a treatment effect, people are different, and chance. We could do the same thing within each group, right? How different the scores are from each other. We can measure that with the sum of squares or maybe the variance, right? Within each group, we can calculate the variance, and we can say this is how much the scores are different from each other, and there's two reasons why. Because of different people within the same group and other effects of chance. And by comparing the measurements of how different these numbers are from each other with the measurement of how different these numbers are from each other, we can use that calculation to help us make a decision as to whether these means are significantly different from each other, and whether their differences, their variability reaches statistical significance. And we do this by calculating Anova. The test statistic for Anova is called F, and F is a ratio. It's the ratio of how different the means are from each other, the treatment means, the group means, to how different the scores within each group are from their individual group mean. And the measurement, as you might have guessed, of the variability we're going to use is the variance, but we're not going to call it the variance, and that's what makes Anova just a little bit confusing. But it's simply a matter of dividing the variance for the group means, right? The variance between the group means, not the variance between the group scores, but the variance between the group means by the variance of the scores within the groups. All right. Analysis of variance is a hypothesis testing statistic, so it follows the same 4 steps that we've been using in the t-tests. You'll write out the null hypothesis, which I'll get to in the next part, We'll determine alpha and find the critical region, and we'll calculate a test statistic, which is F. Finally, we'll make the decision, and then we'll practice writing some sentences and things like that. Okay. So we could measure the total variability, and what we'll find is that Anova, which stands for Analysis of Variance, does exactly that. The word analysis means to split something into its component parts. So how would we measure the total variability of all 15 of our scores? Well, we could use the sum of the squared deviations from the mean. You guys already know how to do that. There's some letters in here that we haven't talked about yet, but you know that the sum of the squares is equal to the sum of the squared scores minus the square of the sum of the scores. And here, G is a letter, it's a new statistic that means the sum of all of the scores in your distribution. So let me go back to the data slide and just show you that all of these scores, 542, 765, 433, 421, 432, that's all of the scores. Their sum total is G. All right, so we can measure the total variability of all 15 of the scores. We could also measure, if you'll go down here to the bottom right, the sum of the squared deviations of each score within a group, right, within a treatment group, from their mean. And if we add all those up, right, we'll get the total sums of squares inside each treatment group, right? Within each treatment group, we add them all up together. And that is part of the overall variability that we measured with the total sums of squares. The other sum of squares that we're going to calculate is the sum of squares between treatments. It's really the sum of the squares for the treatment means times the number of scores that we have. And the way that we do this is we sum the group totals squared divided by n, and we subtract g squared over n just like we do in the total sums of squares. And if you're lost right now, don't worry, we're going to come back to this, all right, in the next video. Well, we do the same thing with the degrees of freedom. We have 15 total scores, and so the total degrees of freedom is 15 minus 1, or 14. But there are degrees of freedom for looking at the differences among the three group means, right? We have between treatment groups degrees of freedom, and this is just the number of means that we have minus 1. And K stands for the number of groups you have. You have as many means as you have groups. Right? So K, we have 3 groups minus 1. We have 2 degrees of freedom between treatments. How many degrees of freedom do we have within treatments? Well, remember we divided the total sums of squares into sum of squares between and sum of squares within treatments. Sum of squares within treatments involved, and I'll go back to the data now, calculating the sum of squares just for the Mozart group. So you subtract the mean from each one of these scores, right? And square that deviation. You add them all up and you have a sum of squares for the Mozart group. Same thing for the relaxation. Same thing for the silence group. We have 3 sums of squares, we add them all together. Within each group we have degrees of freedom. So in the Mozart group we have 5 minus 1 equals 4 degrees of freedom. Same thing for relaxation. 5 minus 1 equals 4 degrees of freedom. Same thing for the silence group. 5 minus 1 is 4 degrees of freedom. If you add all those degrees of freedom within groups together, you get 4 plus 4 plus 4 is 12. There's another way that we could calculate that. We have 15 different scores. We'll subtract 1 from each, 1 for each group that we have. So it's really the total number of scores you have, and that's n, big N, minus the total number of groups you have, which is K. And that's where we get this calculation for degrees of freedom within treatments. It's the sum of all the degrees of freedom within each group, little n minus 1 for the Mozart, relaxation, and silence group. And that's the same thing as taking all 15 scores and subtracting 3. The answer is 12 either way you do it. All right. Let's go back to F again. What is F? F is the ratio of how different the means are from each other, right? It's the variance between the group scores divided by the variance of scores within the groups. Now, the reason that there is variance or variability in the numerator here is because, why? maybe a treatment effect, people are different, and other effects of chance. Why is there variability within groups? Why do people score differently even though they're experiencing the same treatment? Well, because they're different people, and because there are other effects of random chance. So what happens when there's no treatment effect? And that's what the null hypothesis is that there's no treatment effect. What will F converge on? What value does F have when treatment effect is 0 and you're simply dividing variability due to individual differences in chance by variability due to individual differences in chance? Well, you're dividing, it's not 0. So if you're thinking 0, you're wrong. You're thinking about t. It's actually close to 1. So when the null is true and there's no effect, then the variability among these three means, let me go back to the data, will be similar to the variability within each treatment group. And we'll get a value close to 1. Sometimes, though, even when the null is true, just by chance, you'll create groups with means that are more different from each other than the scores within each of your artificial groups. I mean, the null is true, so you're not going to treat them differently. And you'll get much more variability among the means than within the groups. And so even when the null is true, it has a skewed distribution like this, where it's unlikely to get very large values for F if there really is no treatment effect. Okay, so that's what F looks like when the null is true. You could use calculus to find out, what is the actual proportion beyond a particular F score, but you don't need to do that. F values have been tabled, and this is what the F table looks like. To determine the critical value for F, you need to know two things, though. There's not just 1 degrees of freedom that you need to look up. You need to have degrees of freedom in the numerator. Numerator of what? Well, the numerator of the F ratio. Let's go back to what F actually is. Remember, we had variability between the group scores. So there's between treatments degrees of freedom. That's the number of groups minus 1. But you also have degrees of freedom for the denominator term, the variance of scores within the groups, or the within treatments variance. All right, so to use the F table, you calculate the degrees of freedom for the numerator and go across. We actually had 2, right? 2 degrees of freedom because we had 3 groups minus 1 is 2 degrees of freedom for the between treatments variability or variance. In the denominator, we decided we had 15 total scores minus 3 groups, right? Subtract 1 from the total for each group, leaving us with 12 degrees of freedom in the denominator. That's for the between treatments variance. All right, so you go across to the degrees of freedom in the numerator, down to the degrees of freedom in the denominator. And in your textbook, you'll see that there is light face type for the critical values of F at an alpha of 0.05, and bold face type for a critical value of F at an alpha of 0.01. It makes sense that this one would be larger because that means it's harder to find an F value that's that far out. All right, in the next video, we'll show you guys how to actually calculate the sums of squares and then the variances, which we're going to call mean squares, for the between treatments group and for the within treatments group. And we'll see you then.